All right, so now we're recording in case we lose communications. So go back up to here, and that one's in compression, so we'll draw it in red. All right, so I only have one more member that we haven't found the force of, and that is AB. I guess we didn't do B before, we just did C, D, and E. So we could either do A or B. Which one would be easier? B would be easier because there's only one force on B. So we'll do a free body diagram of B. B has two forces. One is FAB. The other is FBC. Because the other two members that came together, they were both already determined to be zero. And FBC we already figured out was 450 pounds. So since my net force is zero, that means FAB is also equal to 450 pounds. Because it came up positive, is it going to be tension or compression? That's going to be in tension. Oh, she's in the physics lab. All right, so that finishes that. Just draw that one in as yellow. So we had 2 tension, 3 compression, and 2 zero force members. So really this truss was a lot simpler than it looked because it's just a single triangle. Really? These 2 tensions are the same because this is really just one long member. These ones here in the middle do nothing. These 2 were the same, CD and DE, because it's really just one long member, and these 2 other ones do nothing. So we could have saved ourselves a lot of trouble if we knew how to recognize those zero force members at the beginning. And if you're drawing trusses and you could recognize zero force members, then you're going to save yourself the trouble of drawing in something that you're going to erase later because it turns out to be zero force. There is a reason why you might want to have one of these, and if you have one, you'd have to have both, why you would want to have these members in here. Anybody think of why we might want to have those members even though they're zero force? Yep. In case the loading changes, okay, so that could be a difference. I might have a load on here, and actually I will have a load on here because we've ignored the weight of the truss materials themselves. So that might be one reason. So we might have to put on some loading to account for the weight of the truss. Another reason might be, in this case, this is only 6 feet. So it's no big deal to put that in as a single piece. But what if it was 26 feet? Right? If you're making this out of lumber, it's pretty hard to get a 26-foot 2x4. But we could easily get, a couple of 13s. Or you'd probably want to break it up into even smaller pieces if you were making it out of lumber. 3 feet's good. 8 feet would be good. All right, so zero force members. So we saw from the previous example that the analysis can be greatly simplified if we can first identify members which support no loading. So the two things we're looking for is, first of all, if there are only two truss members at a particular joint and no external loading, then both members must be 0. Secondly, if there are 3 truss members at a particular point and no external loading, then if 2 of them are collinear, the third must be 0. So if we look at this truss, at joint D, I have 3 truss members, and these 2 are collinear, which means this one has to be 0. Once this one's 0, now when I look at B, there's only 3 truss members left. There's going to be BE, AB, and BC. But AB and BC are collinear, so that means BE would have to be 0. So we could have eliminated those before we started if we were forward thinking. Okay, there's no way of predicting the 0 load from looking at this joint because there's 3 members here, but none of them are collinear, and there's external loading. As soon as you put external loading on the joint, it's going to be difficult to predict a 0 load number. All right. So in this example, it says determine the force in each member of the truss. Identify any 0 force members first to simplify. So can you see any 0 force members in this truss? Okay, so you say B to D. Why is B to D going to be a 0 force member? Right. At B, there's 3 members and 2 are collinear, and there's no external loading. That's key. That makes that a 0. And same thing at joint E. We have 3 members, no external loading, and 2 of them are collinear, so this one would become 0. All right. So this is going to be a much easier truss now to analyze. To analyze this truss, where would you start? Start at F. Okay, that would be a good choice. Why would you choose F? Why wouldn't you start at D or... Right, starting at F, there's only 2 components, so there's 2 unknowns. We get 2 equations of equilibrium. We can solve for those unknowns, and we can move on to the next joint. Okay, so start with free body diagram of joint F. So the forces on F are going to be the 900 pounds. We're going to assume everything's in tension. So there's going to be the member F or EF, or I can call this DF now because it's all going to be one long member. And then there's also going to be the member from A to F. Which we're also assuming is in tension. Okay, from the free body diagram, we would then go to the equations of equilibrium. I might actually have room to put those beside here. So it doesn't matter which order I do them in, but I know I have the one known force and one unknown force here that has a vertical component, so it's going to be easier if I start with y. So forces in the y direction, it looks like they're both negative, which means I've made an incorrect assumption on the direction of this one. It's okay. I'm going to get negative, that means it's compression. So minus 900 pounds, and then minus, I have a 3, 4, 5 triangle here, so to get the y component, it's going to be 3/5 of FAF. So from that equation, we get FAF is equal to negative 1,500 pounds. And because it's negative, that tells us it's in compression because we assumed tension. That Fx equals 0. So both of these are drawn to the right. Okay, but we know that FAF is actually going to be to the left. So we would have FDF and then minus 4/5 of 1,500. Okay, so 4/5 of 1,500 would be 1,200. And is that one tension or compression? Tension. Okay. So this one is in tension. This one's in compression. Oh, yep, that's right. Actually, I labeled it as F. Oops. There. So that part's done. Where should we go next? Okay, so I could go to A, except that I don't know what the external loading is on A. I could have solved for that first, but I don't think I need to. By the time we figured out all of the internal forces, that's going to give us the reactions at A and at C. So if I go to D, then I only have these two unknowns, so I should be able to get them, and then I can go from there to either C or A, where we'll have a tension member and reaction force. Actually, we'd have to go to A first, because C is going to have two reaction forces. First, we're going to do D. You lost? Okay, just a second. Nothing? Oh, now I've lost Campbell River completely. Okay, we've lost Campbell River for a second, but they'll be back. Oh, he's back. Have you got content? Yeah, perfect. Okay, so second part, free body diagram of D. So what's D going to look like? All right, so we've got the tension from F to D, so that's opposite of that. we're going to have the 600 pounds loading, external loading, and then I would have these tensions down. I'll label those. So that's 600 pounds. That's FDF equals 1200. And FAD and FCD. All right, so should we start with X or Y? It doesn't really matter. We're going to end up with two equations and two unknowns. So what have we got in the X direction? I'm going to have 1 in the positive direction. So that would be 4/5 of FCD. And then I'm going to have minus 4/5 FAD. And then I'm going to have minus 1200. Okay, so two unknowns. In the Y direction, I have the same two unknowns. Oh, and it looks like everything's negative. So negative 600 minus 3/5 FCD minus 3/5 FAD. All right, so two equations, two unknowns. We could set up a matrix if we wanted to, or actually this one would probably not be that bad to do a matrix for. Well, I'm going to multiply by 5/4 for the top equation. So 5/4, this augmented matrix would be 1 minus 1, and when I move that to the other side, it's going to be positive, and that would be 1500. And if I move those two to the other side this time, then they're going to be both positive. Multiply by 5/3. That would be 1, 1, 5/3 times 600. 10,000. Probably would have been easier to use substitution, but this is more fun. All right, so now what are we going to do? College of the Rockies, have you done your matrix algebra already?
Yeah.
Yep, awesome. Usually we don't use matrices to solve these simple equations because it's easier to do substitution, but sometimes we're going to end up with systems of equations still that are going to have 4 or 5 unknowns, so we just need to refresh our memories of how to solve those systems. So we've got -1 times this row, add to this row. One minus 1, 1500. 0 minus 2 plus 2 and minus 500. Okay, so from there we know that x2, which is going to be the FAD, equals negative 250. So negative 250 means it's going to be in compression. And then we would substitute back in to find FCD. $1,750. And that's going to be tension or compression. Oh, we lost Campbell River again. Oh, it's back again. That's going to be tension.
Wouldn't it not be 1,250 negative, and then you subtract it? Negative 250 times negative 1 equals 1,500, so 1 for that.
Oh, yes, you're right. Yep. $1,250. Okay. So we got the compression in AD, and we've got the tension in CD. All right, so we've only got one force left, which is this FAC. How are we going to find that? Free body of A, right? Because A only has the one reaction force. So we're going to have the one reaction force and the tension in AC.
You have to worry about the reaction force of A because it would just be in the y direction.
No, but just the fact that there's two unknowns and two equations of equilibrium, so we can solve it. Whereas at C we have two reaction forces and the one tension, so we can't solve at C. So no, we don't actually need that reaction force, but that's where our other equation would go. So we do free body diagram of A. Okay. So A is going to have those two compression forces. So they're both going down like this at a slope of 3/5. We're going to have our reaction force, and we're going to have the tension in this member over here. So this would be AY, this would be FAC, FAD, and this was FAF. So AD was 250. Oop, forgot to put the units in there. And what was FAF? 1,500? Sounds familiar. FAF 1,500. All right. So FAC is the only other internal force. So we could just write the one equation. So the x component of FAF would be 4/5. The The x component of FAD is going to be 4/5, but it's in the opposite direction. And then FAC is to the right. Let's solve that. Negative 1,000 pounds, which means it's also going to be in compression, opposite the direction shown. There, and then that one's done. All right. So these have been fairly simple trusses, right? They're all simple trusses. These have been fairly small trusses, small number of members, small number of joints. If you look at a typical roof truss or a bridge truss, there's a lot more joints than that. So you could just keep following the same procedure through, and if you have to analyze the whole truss, that's exactly what you would do. You'd set up probably a spreadsheet to do the work for you so that you can make changes to the truss design and not have to redo all your calculations. But that's the idea. What if we have a truss and we only want to analyze it so that we can find the forces in 1 or 2 or 3 of the members that we're particularly concerned about? Maybe the truss failed and we want to figure out what force was there that caused it to fail. And we know that it failed on 3 of the web members. Well, then we would use the method of sections. That allows us to calculate the forces in part of the truss without having to calculate everything else. So the principle of the method of sections is that if the truss is in equilibrium, then if we cut away any section of the truss, it's also in equilibrium. So we cut a section through the truss, through the members whose loading that we want to determine. If then I'm only looking at 1/2 of the truss after I've cut it, those forces become external forces to that half. They also become external forces to the other half. We're not actually cutting the truss. We're, in our analysis, doing a figurative cut of the truss. So we determine the truss support reactions first, if necessary, and then we section it, and then we find the cut members' forces as reactions to that free body diagram. And we do the same procedures before. Assume any unknown force is tension, and then if the values come out negative, then we know that it's compression. Solve the equations of equilibrium. This time, because we're doing a free body diagram of a rigid body instead of a particle, we're going to need to take moments. So when we're taking moments, we always want to choose a point where we're going to have the fewest number of unknowns. So if I can take moments about a point where 2 of my unknown forces coincide, then I'm only going to have one unknown in that equation. And that's going to make it easier. If 2 unknown forces are parallel, use a frame of reference parallel and perpendicular to these forces. In other words, move your x and y axis to make it easier. All right, so here's an example. Here's one we wouldn't want to have to solve the whole truss on an exam because there's a lot of joints. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 joints that we'd have to solve to do the whole truss. Chances of doing 12 joints and making no mistakes doing it by hand is pretty low. It looks symmetric, but it's not. It's a symmetric truss, but the loading isn't symmetric, so you wouldn't be able to say that the left side and the right side are exactly the same. So instead, we're going to use method of sections to determine the force in members HI. We just highlight those members. So HI Fi and EF. All right. So to find those forces, where do you think we're going to draw a section? We're going to take a section cut right here. Okay, so before I do a free body diagram of the section, though, I need to solve the free body diagram of the whole truss so I can figure out the reactions at A and G. So that's our first step. Find reactions at A and G. What kind of reaction is there going to be at G? G is a roller. Right, so it's only going to be a vertical force at G. What about at A? Potentially there would be an X and Y component. I can tell by looking at it that the X component is 0 because there's absolutely no horizontal loading. But I'll put it in there anyway because it is a pinned joint and it would support a horizontal loading at A. It is properly constrained, in other words. So that would be AX, AY, and GY. And AX we know equals 0. Okay, so how are we going to find those reaction forces? Right, net force in the x direction is basically what we've already done to find AX equals 0 because there aren't any. So then we would use net force in the y direction equals 0, and I've got two forces that are up, AY and GY, and I've got four forces that are down, which add up to 4 and 5 is 9, and 8 is 17, and 6 is 23. 23 kilonewtons. Okay, and then the other one is going to be a moment. What point should we take the moment about? Right, well, I could do either, because I'm going to get the other one, but if I use A, I don't actually even care about AY, if I only do a free body diagram of this right section. So we would do moments, sum of the moments about A equals 0. So if we start at the left and work our way right, the first one we're going to have is the 4 kilonewtons, and it's 2 meters away. Is that a positive or a negative moment? Assuming counterclockwise is positive. So that would be negative, assuming counterclockwise is positive. So that'd be negative 8 kilonewton meters. And then I'm going to get to the 5 kilonewtons, which is 4 meters away. And then I'm going to get to the 8 kilonewtons, which is 8 meters away. Minus 64 kilonewton meters. And then I'm going to get to the 6 kilonewtons, that's 10 meters away. 2, 4, 6, 8, 10. So minus 60 kilonewton meters. And then finally I'm going to get to G, and I have Gy that's 12 meters away. And that one's going to be positive, or counterclockwise moment. So plus 12 meters times Gy. Okay, so 12, we keep an extra digit here, 12.67 kilonewtons. Okay, and if Gy is 12.67 kilonewtons, then I can also solve for Ay. 23 minus 10.3. 10.3. Okay, so we found the reaction forces. We figured out where we want to draw a section. What's our next section? Next step. Well, our next step is actually to draw a free body diagram just of that section, and then replace all of the cut members with external forces. So we have a choice here. We could do either the right section or the left section. Which one's going to be easier? The right section is going to be easier because there's only going to be one external force, well, two external forces, because there's going to be the reaction at G. But it's definitely a lot simpler. So we'll draw a free body diagram of right section. So my right section is going to look like that. All right. So all of these cut members become external forces. I don't want those to be dashed. Okay, so this was Gy equals 12.67 kilonewtons. And this is going to be FHI, FFI, and FEF. All right. What do we want to do next? Okay. That would be using the method of joints. So we're using the method of sections. So we're just using the one free body diagram here. So we're going to treat this as a rigid body, and we're going to have three equations of equilibrium. Have our x equals 0, that Fy equals 0, and the net moment about some point equals 0. So my question would be, what would be a good choice of a point? Okay, why would we choose F?
Because it gets rid of 2 of the unknowns.
Because it gets rid of 2 of the unknowns, and it also gets rid of 1 of the known forces. So if I choose F, then the only forces that are going to produce a moment are going to be Gy and Fhi. So moment about the point F equals 0. We're going to start with that one. So which force is going to cause a positive moment? Gy. So that's going to be 2 meters times Gy, which is 12.67 kilonewtons. And then we need to figure out the moment produced by this force. And we remember from the diagram that this is a 3, 4, 5 triangle, these members. So this is 1.5, and this is 2, and this is going to be 2.5. So to figure out the moment, I can either use the horizontal component and this distance, or I can use the vertical component and this distance, and they're going to come out to the same thing. So if I use the vertical component, that would be 3/5, that'd be 2 meters, times 3/5 Fhi. Oh, yes, it is positive as it's drawn in the diagram. You're right. They're both positive, which means one of them's wrong. There's only one that's unknown. All right, so I can solve that one then for Fhi. Yep. Negative 21.1 kilonewtons, which means it's going to be compression. Okay, so now I've got 2 unknowns left. Which equation should I do next? I would do y next as well, because y only has one, there's only one of the remaining unknowns that has a y component. Okay, so net force in the y direction equals 0. I'm going to have 12.67 is up, 6 kilonewtons that's down. I'm going to have the y component of Fhi, which is going to actually be down because it was in compression. So minus 3/5 of 21.1 kilonewtons. And then I have the vertical component of Ffi. So how am I going to figure out that? So this one goes over 2 and up 3. So I could figure out the angle, or I could figure it out as I could figure out the sine and cosine as a ratio. Doesn't matter which. So what's this angle going to be equal to? So that'd be the inverse tan of 3 over 2 equals 56.31 degrees. So if we're looking for the vertical component, then that would be sine 56 6.31 degrees. So there's only one unknown in that equation, so it should be easy to solve. I have 7.2 as well. 7.2? Okay, majority rules. 7.2, 7.20? 7.20 kilonewtons. Okay, so now we've only got one force left. So now we'll go up to the forces in the x direction. So what have we got in the x direction? I've got the x component of FHI, which is actually going to be positive because that one was compression. This one's tension. So that would be 4/5 of the 21.1. And then I'm going to have the x component of this one, which is going to be negative. That's going to be negative 7.2 kilonewtons cos 56.31. And then I have FEF, which is just straight to the left, so minus F. So we get a positive value, so that one's also going to be in tension. All right, so we were able to solve for those three without having to do all of the... Actually, in this case, because the three were close to the end, it probably would have been just as easy to start at G and then work our way over, which I think was what Dylan's suggestion was. But if it was anywhere in the truss, use method of sections to find at most 3 unknowns. All right, so here's an even uglier truss. Well, it's not an ugly truss. It's quite an attractive truss. But it's got lots of nodes in it and lots of members. So this time we want to determine the force in members CD, LD, and KL. So first we'll highlight those. So CD, LD, and KL. So if we want to figure out those loadings, we would basically cut the truss figuratively right through those 3. Okay, but before we cut it, we're going to figure out the reaction forces at the 2 ends, which again are A and G. So 1, find reaction forces. Okay, what's the nature of the reaction force at A? Right, because A is a roller, that means it can only support a normal force, which means it's going to be upwards. So call that AY. G is a pinned joint, so it can support a force in any direction. So we'll divide that into its x and y components. And yes, I know that ax is going to be in the opposite direction, but we're going to get a negative value that's going to tell us it's in the opposite direction. So I got it as ax, sorry, gx and gy. All right. What next? Equilibrium for the whole truss. So we would look at the net force in the x direction equals 0. So we have one support reaction in the x direction, and we have one horizontal loading. That tells us Gx equals negative 900 pounds. It's a reaction force, so it's not tension or compression, it's just opposite the direction that we've drawn it. So it's going to be to the left. Our other equations of equilibrium would be net force in the y direction equals 0. And we have two support forces, AY plus GY, and we've got three vertical loadings, which looks like 3,500. Okay. And then we're going to have moments. I think I'm going to go underneath to write the moment equations because it's going to be easier. What point would you like to take the moments about? G would be a good choice, right? Because then I get rid of two of these unknowns. Well, one of them's known now, but still I get rid of two of them. Okay, so if I move away from G, the first external force that I get to is the 1,000 pound force at Y. What's the moment going to be produced by that force? Right, it's going to be the 16 feet, the horizontal distance times the vertical force. So it's going to be 16,000 foot-pounds. Then I'm going to get to the 1,500 pounds, which is a distance of 24 feet away. And then we get to a 1,000 pounds, that is 32 feet away, so that'd be 32,000. And then we get to this 900 pounds. Is the 900 pound force going to produce a moment? Yes, it's going to be a moment because it's a vertical distance of 24 feet. And is it going to be a positive or a negative moment? That one's going to be negative because it's clockwise. So minus, how much? 21,600 foot-pounds. So that's the 24 times the 900. And then the last force we're going to get to is AY. And is that going to be positive or negative? Negative. So minus, and the distance is 8, 16, 24, 32, 48. Minus 48 feet times AY. All right, so we can solve that for AY. 10,300?
1,000.
Oh, I'm looking at the wrong one here. 1,300, yes. 1,300, and the units are ounce. Okay, so from that we can also then solve for GY. From our earlier equation, GY was going to be 3,500 minus AY. So that leaves 2,200 pounds. All right, so I finished equilibrium of the truss. What's our next step? Well, I could do either the left side or the right side. Looking at it, the left side looks a little bit easier. Not really that much. The left side's going to have 1, 2, 3 external forces on it that I know, and then it's going to have the 3 unknowns. If I look at the right side, there's going to be 1, 2, and then there's 3, 4. There's one more external force. So it's slightly easier to do the left side. It's not incorrect to do the right side, but in general, we want to always try and make it easy. So our next step would be to draw our free body diagram of, this time we'll choose the left section. So my left section will be right there. I think we're going to go onto a new page for that. All right, so we've got the left section has these 3 forces on it. At each member that's cut, we're going to draw the reaction forces, or the forces in those 2 force members. We're assuming they're all in tension. So this one was FKL, FDL, and FCD. Okay, so we've got the free body diagram. Now we're going to solve for equilibrium of the section. If we were to take moments, which point should we take the moments about? Okay, why would we take moments about L? Yeah, it's going to simplify a great deal. The moments about L, I could choose any point. This is just going to make it easier. So a moment about L equals 0. FCD is going to produce a moment about L. Is that going to be a positive or a negative moment? Positive. So that's going to be FCD times what distance? So it's this 8 feet times 8 CV, FCD, so 8 feet, FCD. These are both 0, these are both 0, The only other force I have is AY. Is that going to produce a positive or negative moment? It's going to be negative, right? Because it's going to be clockwise. And what distance am I going to use for the... It's a vertical force, so it's going to be the horizontal distance, which is 16 feet. And AY, we already know, should write that in, equals 1,300 pounds, 1,300 pounds. And just like that, there's FCD. 2,600 pounds, tension or compression? Tension, because we assumed tension and it came out positive. Okay. So to find the other two unknowns, we're going to use the other two equations of equilibrium. Which one should we start with? Okay, I could start with forces in the x direction, but then I'm going to have two unknowns. Because both of these unknown forces have x components. So if I start with the y direction, then I only have the one unknown. So that's going to make it a little bit easier. It's not wrong to write the other one down first. It's just we're not going to be able to solve it until we've done forces in the y direction. So forces in the y direction, I've got AY. I've got the 1,000 pounds. And then I only have the x component of FDL. And was that 45? Yeah. So minus FDL sine 45. Okay, so 424.3 pounds. Is that in tension or compression? Tension, because it came out positive and we assumed tension. Sum of the forces in the x direction. What have we got? I've got 900. Right, so I know FDL, so I can figure out its x component. So plus 424.3 pounds cos 45. And then plus FCD, 2,600 pounds. And then plus FKL. So since everything's positive, I have a feeling FKL's in the opposite direction. Negative 3,800 pounds, and because it's negative, that tells us it's opposite the direction assumed, or it's in compression. Alright, so if we go back, we used the color coding we were using before. These two are in tension, so we draw them in yellow. And this one's in compression, so we draw it in red. All right. The next section is, it's really interesting, but as far as exam type questions, it's really hard to put them on there because instead of ending up in systems of equations where we've got two equations per joint, a space truss is a truss that's in 3 dimensions. So instead of being in a plane, you've got members that are in 3-dimensional space. So instead of being made up of triangles, it's made up of tetrahedrons, right? So a tetrahedron is made up of 4 triangles that come together at common endpoints. So the structure composed of slender members joined together at their endpoints to form a stable 3D structure. It's going to look something like this. So at each joint then, if we're using the method of joints, instead of having 2 equations, we'd have 3 equations, which means we can solve for 3 unknowns. If we're using method of sections, instead of having 3 equations of equilibrium, how many are we going to have? 6, right? So we'd be able to cut a section that goes through any 6 of the members. So these get complicated really quickly. So all the examples that are in your book and the examples we're going to do in class are of reasonably simple space trusses. If you're actually doing the design, you'd want to set up a spreadsheet that was going to do the calculations for you. And this is a big space truss. I think this is one of the Olympic buildings in Beijing. So this is a big arch that's made up of a huge space truss. Yeah, it was quite the spreadsheet, I'm sure. All right, so the procedure for analysis is actually quite similar. So method of joints, 3 equations of equilibrium instead of 2. Start at a joint with at least 1 known force and at most 3 unknown forces. So similar to what we did with the method of joints with the planar truss, except we're allowed to have 1 more unknown. And if the geometry is hard to visualize, then we want to break down all of the directions into Cartesian. Basically, we want the unit vectors for the directions, so then we can put them into their x and y and z components. If we're using method of sections, so we only want to find a few members instead of the whole thing, we do the same thing, but our section cuts the truss into 2 parts, each of which must satisfy the 6 equations of equilibrium. We're not going to do any method of sections with the space truss. So here's a fairly simple example. We've basically just got a single tetrahedron here, so that's the simplest space truss that you can have. And we want to determine the force developed in each member of the space truss and state whether the members are in tension or in compression. The crate has a weight of 150 pounds. And you notice the reactions at the points A, B, and D where the space truss is attached to the wall. There's a reason why one of them is just a simple simple pinned joint, and the other 2 have 2 force members that are attaching it, and that's to make sure that it's not over-constrained. By having member B attached by this 2 force member, that means there's only 1 component of reaction at B. By having the 2 force members at A, that means there's only 2 components of reaction at A. And at D, we would have, it's a ball and socket joint, we'd have 3 components of reaction. I don't actually even care what the components of reaction are, because I can start at C. Right? C has 1 known force, which is going to be the weight of the box, and 3 unknown forces, which are the other 3 members, or the 3 members that are at that point. How's our time? 3:45. So we'll be able to set up the equations for the first joint. That's probably all we'll get through today. So, where should we start? At C. Free body diagram of C. Free body diagrams, my free body diagrams are a little bit more, a little harder to follow in 3 dimensions. That's okay, because we're gonna write the directions of those forces on there. So if we have C, I know I have one force that's going to be the weight. So that's 150 pounds. Oops. Okay, and then I've got the 3 members, which I'm assuming they're all going to be in tension, that are attached at C. I've got FCD, which is horizontal. I've got FAC, which is going to be down towards A. And I'm going to have FBC, which is going to be down towards B. All right, so we're gonna come up with unit vectors for the directions of all of these. 150 pounds. What direction is that going to be in? It's going to be negative k. Yeah, so I have negative 150 k hat. What's the direction of FCD? It's going to be negative j hat. So we have negative FCD, which is its magnitude, times j hat. And FBC and FAC are going to be a little bit more tricky. So we would have to start by going, FAC is going to be directed from C towards A. So we look for our position vector first from C to A. And how far do we go on the x-axis? On the x-axis, we would go positive 3, because this is parallel to the y-axis. This is 3 feet over, because this is an equilateral triangle. So that'd be 3 I hat. And on the y-axis, be minus 6 j hat. And on the z-axis, how high is this? Root 45? Root 45. No, sorry, you're right. You're right. Yes. Root 27. So root 27 k hat minus root 27 k hat. Okay, so if we want to put that into a unit vector, we would divide by the square root of this squared, so that'd be 27 plus 36 plus 9. 27 plus 9 is 36, plus 36 is 72. So we'd have 3 over root 72 I hat minus 6 over root 72 j hat minus root 27 over root 72 k hat. Okay, and then we can say down here FAC times the unit vector from C to A, and that would give it as a Cartesian vector. FBC is going to be FBC times the unit vector from C to B, and that would put it as a Cartesian vector. And we are out of time, but UCB by symmetry, UCB is going to be exactly the same, except the x component is going to be in the opposite direction. So we'll finish this up next week. Oh, yes. For NIC students, your quiz will be available anytime tomorrow. You have an hour to complete it. I'll put in an announcement, post some suggested exercises you might want to look at before you start the quiz. It shouldn't take you an hour.